The limits of logic. How Kurt Gödel redefined mathematics in the early 20th century, mathematicians believed they were on the verge of a monumental achievement: the creation of a perfect, self-contained system of logic that could explain everything. They envisioned mathematics as an infinite engine of discovery, where every true statement could eventually be proven through a rigorous set of rules. Then came Kurt Gödel. By proving that mathematics is inherently incomplete, Gödel did more than solve a problem. He fundamentally altered our understanding of human knowledge. He proved that there are truths that exist beyond the reach of proof, effectively setting a permanent boundary on what the human mind can formally verify. The quest for certainty. Hilbert's dream to understand the impact of Gödel's work. One must first understand the ambition of his predecessor, David Hilbert. At the turn of the century, mathematics was facing a crisis of confidence. Paradoxes were emerging that threatened to undermine the very foundations of the field. In 1900, Hilbert proposed a grand research program to rescue the discipline. His goal was to establish a proof theory that would ensure mathematics was consistent. A set of rules axioms would never lead to a contradiction, e.g., proving both that 1 + 1 = $2 and 1 + 1 = 3. Complete. Every mathematical truth could be derived from a finite set of starting rules. Hilbert's philosophy was one of supreme optimism. His famous mantra, "We must know, we will know," encapsulated the belief that no problem was too complex for human reason to eventually solve. The breakthrough, the completeness theorem. In 1930, a 24-year-old Kurt Gödel presented his completeness theorem. At first glance, this seemed to support Hilbert's vision. Gödel demonstrated that for any given set of axioms, if a statement is true in every possible mathematical model of those axioms, then that statement is provable. In simpler terms, he showed a strong link between truth and provability. This was a major step forward, suggesting that the mathematical world was indeed a coherent and navigable place. However, this success was merely the prelude to a much more disruptive revelation: the Great Disruption. Gödel's incompleteness theorems. Just days after his initial success, Gödel began to unravel the very foundation Hilbert sought to build. Through his incompleteness theorems, published in 1931, he delivered two devastating blows to mathematical optimism. The existence of the undecidable Gödel proved that in any sufficiently powerful mathematical system, there will always be statements that are undecidable. These are propositions that are true, but cannot be proven true using the rules of that system, nor can they be proven false. This is similar to the logical paradox: "This sentence is false." It creates a loop that the system cannot resolve, proving that truth is a much larger category than provability. The impossibility of self-verification, even more damaging to Hilbert's specific goal, was Gödel's second theorem. He demonstrated that a mathematical system cannot prove its own consistency. To use a board game analogy, you can study the rules of the game as much as you like, but you can never use those same rules to prove that the game won't eventually produce a contradictory result. To prove a system is consistent, you would need a more powerful system of rules, which would then require an even more powerful system to prove its consistency, leading to an infinite, unresolvable chain. A legacy of rich poverty, the reaction from the mathematical establishment was telling. While Gödel's work was undeniable, the giants of the era, like Hilbert, struggled to reconcile it with their worldview. Hilbert's public responses were dismissive, attempting to frame Gödel's findings as errors rather than fundamental truths. Ultimately, Gödel won the intellectual battle. Incompleteness is now a cornerstone of modern logic. While this realization ruined the dream of a perfect, all-encompassing mathematical machine, it also provided a deeper, more nuanced understanding of reality. Mathematics is not a closed loop that can be mastered and finished. It is an open-ended landscape where some truths will always remain just beyond the horizon of formal proof. Conclusion: Kurt Gödel transformed mathematics from a pursuit of absolute certainty into a study of inherent limits. By proving that logic cannot explain itself entirely, he revealed that the mathematical universe is far more vast and far more mysterious than we ever dared to imagine.